Designed and built the electrical and avionics systems, as well as acted as project manager, leading to the qualification of MSS for the $15,000 Lunar Lander Challenge. Ben attended Iowa State University for computer engineering and was the vice president and astronomy chair of the Iowa State Space Society, then the vice chair and member of the year of SEDS. Okay, and I'd like to introduce Ben Brockert.
Do you guys mind if I just speak up rather than use a microphone?
I mind.
Okay.
They can actually hear you better.
Oh, okay. Then I will use the microphone.
If you don't.
Oh, that's no problem. So hello, I am Ben Brockert from Masten Space Systems. As mentioned, I have many jobs there, and we're going to get into that some more. So, my presentation is kind of crap, but
Well, at least you're honest at the beginning.
hey, it works. This is cool. I bought this computer like 2 weeks ago, so it's the first time I've had a chance to play with it. Bought it in the middle of LLC. So, okay, so we are Masten Space Systems. There is a standardized blurb from some of our marketing materials. We do aerospace R&D with the ultimate goal of flying suborbital payloads. The first major target is to put 100 kilograms to 120 kilometers. The idea is that we build things that are totally reusable and sorry, one moment.
Fully reusable presentation.
Yes.
That chart always works.
There it is. Yay. Yeah, so totally reusable, rapid turnaround. We're going to enable an entire new market. And then currently, if you want to fly something in a suborbital payload, you basically sign up roughly a year in advance. It costs you about $1 million. You fly it once, and chances are you don't get your payload back. So with ours, doing completely reusable vehicles, the idea will be that you put your payload on, it takes off, we're all vertical takeoff, vertical landing. We fly it up under power, you coast over the top, you get really high quality microgravity for however long it happens to be on the trajectory we're flying. And then it comes back down, you use aero surfaces and stuff to slow down the drag, or slow down the vehicle using aerodynamic drag, and then relight the engine and land right back on the same pad. And then we can hand you your payload back, and if you say, hey, our experiment didn't work, we say, okay, we can fly it again tomorrow. Basically, be able to do things that so far don't exist at all in the microgravity research thing. Another buzzword that's been around a lot lately is the ignorosphere. Basically, the portion of the atmosphere above where planes can fly, but below where all of the satellites are, that has not been researched very much, just because it's fairly hard to get to. So, because we're doing vertical takeoff, vertical landing, and we have an engine that we can relight, we could theoretically do a trajectory where we fly up and then hover at some random spot in the atmosphere, do sampling for 30 seconds or whatever, turn the engine back off, and then drop back down and land. So reusable, rapid turnaround, reasonably priced, and then we obviously, for it to be reusable, we have to focus a lot on reliability. So a lot of our work has been trying to make sure that everything we build will continue working, getting rid of elements that turn out to be trouble, and there are certainly a lot in rocketry. So here, this is a static engine test. We have this is our 750-1 rocket engine. We have a horizontal test stand, which is actually just a trailer. It looks like a hot dog stand. All of our engines run on liquid oxygen and isopropyl alcohol, which are very benign propellants. You can stick your hand in isopropyl alcohol. I mean, it's rubbing alcohol that you get at the store, just 100%. This is a special run because we were trying out an aluminum pintle. The pintle is the type of injector element we used, and it didn't actually survive the run. So the white flashes are part of the rocket engine melting and going into the exhaust. It kept running though, it just actually just melted the tip of it off. So this engine is copper and stainless steel, and some nice white flashes there. Yeah, aluminum burns white, very bright. Our current engines that we're flying our vehicle with are all aluminum in terms of the thrust chamber and the jacket. We do regenerative cooling, which means that you take the fuel, it goes in at the bottom of the jacket and then flows up the outside of the chamber, basically. So it cools off the chamber. We're the first ones to ever fly a fully reusable aluminum chambered rocket ever, so that's pretty cool. The advantages of aluminum are that it's very light, obviously, compared to copper. It's very cheap to machine. The really good coppers that you want to that are classically used in rockets have about the consistency of chewing gum, and the machinists hate them because they're almost impossible to cut through. So our vehicle projects, we have two vehicles right now. Previously we had a vehicle called XA0.1, which crashed in December 2 years ago, right before I started. One of my first things was to take that apart. So we have two vehicle projects, one called XA0.1E, which we built from scratch. This is the first LOX tank we built. It was a fairly interesting process of building this. The aluminum is a new alloy actually built for high-performance yachts developed in Europe. So we actually bought the aluminum from a company in the Netherlands, had it shipped to a company in Canada where they make it in hemispheres, and then had it shipped to another company in LA where they actually weld them together into a tank, and then to another company that does our hydro testing. So this was the very first one we built. The objective was for it to burst at 1200 psi or better, and it made it up to 1400 psi, so that was a really solid accomplishment there. Really thin spun tanks, the welding is fairly challenging, as evidenced by these. So this was August 31st of this year. The tank on the right was supposed to be the flight tank for XA0.1E. Both of these burst at 800, 900 psi, when we want to operate at about 600 psi. In our stuff, we want to have a factor of safety of 2 over burst, which means that if we're operating the tank at 600 psi, we want to know that the tank is not going to burst at least 1200 psi. And so we basically make the tank and then we hydro test it to 1.5 factor of safety. So if we're running at 600, then we have to run it up to 900. Both of these bursts right in the 850, 900 range. So the general architecture is, like I said, 2 hemispheres spun out of 5mm aluminum with manifolds on the top and bottom. And then that ring around it is how we mount the other tank to it, which here it sort of looks like sunglasses. And then the legs on that one are actually where the engine frame attaches, the engine module. So that was August 31st, and that really put us in a bind because that was August 31st. I guess I should mention, we were competing in the Centennial Challenge's Lunar Lander Challenge, the Northrop Grumman Lunar Lander Challenge, for which the deadline was October 31st. And so to lose our main tank in August was a fairly major setback, and so we were scrambling. But before we got to Zoe, we were working on XA0.1B, or B, or Zombie, as we call it sometimes. The general the general layout is that on the top there's a IPA tank, isopropyl alcohol. On the bottom is a LOX tank, the white one that's insulated. And then on either side there's helium tanks that we use to pressurize the propellants. The interesting thing about the tanks on this one, the fuel tanks, is that they're actually surplus tanks used on the Atlas missiles in the 1950s. We actually got them at Norton Sales down in Burbank. If you're ever in Burbank, you have to go to Norton Sales and wander around. They have rocket engines and rocket tanks and random parts you don't recognize and tubes that say stuff about launch abort system and just all kinds of, it's the greatest engineered geekery place ever. And then the single 750-pound thrust engine on the bottom. This vehicle was actually originally designed to hold 4 500-pound thrust engines. And then in April, very early April of this year, we actually finally burned through one of the engines. It was an old design, it had some major problems, and so we were finally able to get rid of those, basically. And So over about a month and a week, we switched this vehicle from being a 400 or 500 pound engine vehicle into a single 750 and flew it for the first time in May. So, which was the first time our company had ever flown anything. So that was a really good step up. The frame is steel. This one was very much not built for performance. The yellow frame that you can see is TIG welded together steel that I actually welded together. I actually taught myself welding on a rocket vehicle. As she mentioned, I did all of the electrical system on this, which So, but I did on the very top, there's a silver box, we call it the brains. It includes the GPS, inertial measurement unit, has 3-axis accelerometer and gyroscope, and is what lets it know where it is in space and what it's doing basically, and then also it sends all the controls to the hinges. For control, we use a 2-axis gimbal system, meaning you can point the engine up to 21 degrees in the corners, which is a wild, crazy amount of authority. Meaning we could basically do the vehicle, do a flip pretty thoroughly if we wanted to. And then there's, on the edge of the tank, you can see the little brass RCS engines, which are just solenoid valves that shoot out a whole gas, put about 4 pounds of thrust, and that gives it a torque. So that we can spin the vehicle around or stop the vehicle from spinning while it's flying. So yeah, B was originally not meant for performance. Like I said, it originally had 400 or 500 pound thrust engines. We were thinking we'd get maybe 30 seconds of power time on it. And then as we were converting it over to the single engine, a lot of different things fell out. Like originally it had 2 gas system. We had nitrogen to pressurize the fuel because nitrogen is really, really cheap, and then helium to pressurize the LOX because helium is the only thing you can pressurize LOX with because everything else just turns into a liquid when you spray it into it basically. So. One thing that you wouldn't really think about is that one of those tanks full of nitrogen versus full of helium, the nitrogen itself weighs about 12 pounds. So we were able to save 12 pounds simply by switching what the gas was in the tank. And then we also, after we figured out what was necessary and what wasn't, we were able to vastly simplify the plumbing system and just generally reduce the performance or the weight of the whole thing and increase the performance. And now, despite having a heavy steel frame and a bunch of other non-optimized things, this vehicle can fly for about 100 seconds. I forgot to mention earlier, if you ever have any questions, just yell or wave or anything. I'm perfectly happy to be interrupted during the presentation. Let's see if I missed any videos yet. No. All right, so we did the first Lunar Lander Challenge attempt on September 16th for the level 1. I have videos of that I will play. This is our first attempt at level 1. This is just looking straight up in the air, and the vehicle is taking off on the left. So there's 0.1B. There's the kickover that's starting sideways, and there, go back. It's flying about 50 meters straight over the camera, and this is what's called the green flash. Copper, when it melts and burns green. And when your chamber is made out of copper, you really don't want to see copper. You know, it's generally a bad thing, so we'll play that again. Like I said, we did do a kickover maneuver at the top, fairly aggressive. It tips the vehicle over about 10 degrees to give it some lateral velocity, which I found surprising. And it looks cool, too. So, yeah. here's that same attempt on the down looking on board camera. That didn't work. So this is, the engine itself is up there in the corner, and this camera is just looking basically straight down. And this is our concrete tires. So it takes off, and then there'll be some green flashes right there, which means we started having problems. It's actually possible that we damaged it before. We didn't actually inspect it before this flight. We didn't do the crash, but this is what I mentioned about, you really need fault tolerance and something that you need to be reusable. So despite the fact that the engine was eating itself while it was flying, it still kept flying and was able to keep up its performance high enough that it managed to complete the full trajectory. So there's our middle pad. And there's our destination, which has never ever been landed on at this point. So the general LLC trajectory is to go up 50 meters, over at least 50 meters, and then back down. You have to carry a 25 kilogram payload. For level 1, you have to have a full hover time of 90 seconds. And for level 2, you need 180 seconds, so 3 minutes. The level 1 is represents about 1 kilometer per second delta V. Level 2 is about 2 kilometers per second. So for level 2, that means you basically, it's actually slightly more delta V than necessary to go from lunar orbit to sitting on the surface of the Moon. And then we have to refuel it and do it again, and do the entire do it twice within about 2 hours. So, and then we strip that X-Prize logo right off the concrete. It's a nice molten concrete. You can see that the engine gets a bit twitchy at the end of the flight. The vehicle weight goes from something like 800 pounds down to about 500 pounds during the flight. So the entire control system changes, and this vehicle we didn't have really great models of, so it, So that was, something else.
So Ben, that was like the second flight of that vehicle?
No, that was the 33rd flight of that vehicle, or 34th flight of that vehicle. So, I mean, we had a lot of testing in it. We iterated the engines a bunch of times, trying to reduce the, in a regen cooling, you have a trade-off. On the one side, you have how good the cooling is, and on the other side, you have the pressure drop through the jacket. The higher the pressure drop, meaning the difference between the pressure that goes in and the pressure that comes out of the jacket before it goes into the ejector. The higher the pressure drop, then the more pressure you have to have in your tanks, and basically the more performance you're wasting. So we cut it down, and we cut it down too much, which is why we had the problem with the chamber. So go back to this one for real quick so you can see that photo again. So this is looking into the rocket engine after we took apart the chamber. This is looking up the nozzle. The center hole is where the pintle goes. We use pintle injectors, which is a type of injector, and the other hole is where the igniter goes. But so this is supposed to be completely round. This is the inside of the chamber bulging inward, and so it would bulge in, and this melted bit is where the green flashes came from, and there's another one on the top. I've never shown that photo to anyone, by the way. So and it cracked. So it actually, where the fuel is supposed to be traveling at really high velocity up the sides on the outside of the chamber. Here, because it bulges in, it basically stagnates, which means that once it bulges in, then it just keeps wanting to bulge in farther because the cooling just goes to crap. So, and eventually it chewed through far enough that it was actually leaking fuel in through there, which basically arrests the bulging, because then the fuel leaking in causes essentially film cooling. So yeah, like I said, it's a pretty miserable failure. You don't want it to look like that, but it still managed to fly the entire trajectory with an engine that at the end looked like this. So that was an accomplishment. So that was September 16th of this year. September 23rd, so there is our, we made some fixes to the stuff to make the welding job easier for the welders. So September 23rd, this was the state of Zoe. They were just starting to insulate the LOX tank with cryogel. The white stuff is just some sealant. That's Mike, one of our guys, and that's Dave Masten, the CEO. so they were sticking on the landing gear and working on the LOX tank installation. So that was September 23rd. This is what it looked like on October 12th. So basically, in not very much time at all, we went from, well, there's the tank upside down, there's the tank with the legs on it. So we did an incredibly fast vehicle integration. It was about a month from first hardware to having a fully integrated vehicle, which was like crazy fast.
That's about 100,000 times faster than NASA.
Yeah. So, so the top tank is carbon fiber. We decided to try a carbon fiber tank to reduce the weight of the fuel tank because it's not cryogenic. It doesn't need to be aluminum. That turned out to be another issue that we'll get to later. It uses basically the same carbon fiber pressure in tanks. They're DOT rated to 1850 psi. We hydro them up to 4500 psi, so we can run as high as 3000 psi if we want, which is like scary pressures of gas. Like if hoses come off, they kill people kind of pressure. So I really don't like the really high pressure gas stuff. But and then for this one, we just use a simple aluminum tube truss structure between the two tanks to give you the separation. And then there's a computer on that as well. I don't know if you can see it on here, but so there's what the engine module looks like on this vehicle on this day, on the 23rd, 12th. So like I said, this is the fuel line. We inject the fuel into a manifold in the bottom of the engine, and then it flows up the inside between the jacket and the chamber, which gives you the cooling. The big box has sensors in it. We measure chamber pressure, injector pressures, and a pressure switch for the igniter. The igniter is on top of the engine, kind of hard to see. This big thing on the side here is the IPA throttle valve. The fuel throttle valve has a gear motor on the side of it. We just use it's a 12 volt. We run a 24 volt DC motor. And we use H bridges to be able to move it forward and backward really accurately and really quickly. It's basically a homemade high strength servo. Then the LOX valve is similar, but it's mounted directly to the top of the engine up there. And then in the back you can sort of see the hinges, which are ultra motion. They're just linear actuators, crazy strong. Like we've had some issues, and you can actually basically shake the engine apart if you do the programming wrong. They're really, really strong. So after our failure for the first one, we did a whole bunch of tests. Did a whole bunch more tests on the engine. We set up our times. We had 3 attempts at the Lunar Lander Challenge, level 1 and 2. We had 1, and then 3 weeks later we had 1, and then 3 weeks later we had the last one. So in the 3 weeks in between, we reran a bunch of testing on the horizontal stand, like I showed before. I came up with a cooling fix that works really well, and we were actually able to run the engine all the way to stoichiometric, which means it's basically running as hot as it possibly can. And it was able to run as hot as it possibly can and still be in really good shape. So that worked well. And so instead of the copper, which is more classic for our level 2 attempt, our second one, we went with the aluminum chamber, and it went really well, as I will show. Yeah, sorry I have to keep switching back and forth. So this is the first flight, or the second flight, of the level 1 attempt. Some really nice mock diagrams. This was shot by Mike Masten, who's actually an employee of Export. We had him come over and shoot video and photos of us of the flights because we're all too busy. So here's the aforementioned kickover, using some lateral velocity, so you can fly sideways. Really nice chrome. I mean, really, really steady. You'll be able to see it when it goes to drop to reduce its altitude. You'll be able to see lockdown and suck in as it throttles down. The distance between lockdowns is dependent on the size and pressure, basically, of the plane. So they're coming in and back out. So I'm starting the descent. And like I said, you can kind of see a rattle. We didn't have as much time as we wanted, but the tiebreaker basically for the Lunar Lander Challenge was accuracy. So this was a fairly tightly wound controller, basically. It really, really wanted to land really, really close to the center. So for the lunar lander challenge level 1. Our average accuracy was 16 centimeters, which is about that much, which is better than anyone's ever done before or since. So.
Ben, is the navigation entirely on GPS?
It uses, I mean, we have the IMU, but the navigation is all GPS based. We use a differential GPS system, gives us 2 centimeters or better accuracy in terms of position. And just like I said, and then we have to do it twice in 2 hours and 15 minutes, which adds a whole other dimension of challenge because not like it's not hard enough.
So what was the rationale of the aggressive pitch up that you guys do?
Well, it's simply just that you're hovering and you need to go somewhere and no reason to mess around with it. So you want to get lateral velocity, and he simulated everything a lot, and so it just works. Some people were somewhat taken surprised by it because we didn't really brief on the trajectory quite as much as we should have. So it's like I knew it was going to kick over, I didn't know it was going to kick over that much. And when you're standing on the ground, it easily looked like it was 20, 30 degrees. It was only actually 10 degrees. But basically, you have to use the main engine to get where you want to go. You can't use the RCS to move around. You just use that for rotation. So the only way to get moving that way is to actually tilt the vehicle that way. And so you tilt the vehicle that way, and then give you some momentum that way, and you just kind of throw yourself over. So, yeah.
Yeah, was the rocket being controlled, the trajectory of the rocket being controlled externally, or was it an autonomous control?
For these flights, it was totally autonomous. We did, at one point, make it so that we can run it with a joystick, which some of the other teams like to do, but my view on it basically was that it's an amazingly precise robot with way better senses than a guy standing on the ground has, so let the robot be a robot.
Yeah.
Let it do what it does better than we can do it. I mean, with you sitting on the ground, you have no idea basically where it is or what it's doing. And so as long as, I mean, we have people on the ground, I mean, there's still controls. We have 2 different levels of abort. If something goes wrong, the guy with the laptop, Ian, the pilot, well, even though it's flying itself, it's not the pilot, but he can hit soft abort, which just means land the vehicle immediately wherever you happen to be. And then we have other guys with buttons that vent the tanks and turn off the engine and just basically kill the vehicle, and we'll just drop it wherever it is, which we have so far not done. So here's so that first one was the first flight with Fidelity. This is the second one. Because I wasn't a button pusher that day, or I'm calling crashers, I was able to just shoot handheld video, which actually starts, I had to talk on the radio, so it starts in the middle of the flight, or at the beginning of the flight. And then there's a nice nose shot as I blow the dust off of the camera, because I dropped it in the dirt right before the flight. So. But this one gives a bit more of a mood of what we're doing, and what it looks like when you're standing there. There's me. It's really great. I mean, and at the same time, it's amazing how quickly flying rockets gets boring. Because like I said, this was like almost a 40th flight on this vehicle. Though it was only like the 4th free flight. And the free flights do have more of a scare factor to them. So it translates back over and just, flies in trajectory perfect. And after the whole thing, basically I had no bugs outstanding. And really performed well. So it starts doing a descent, and like I said, this vehicle is about 1 kilometer per second in Delta V, which means that if it was in free space, and you just turn the engine off, the blast kept going. At the end, you'd be traveling at about 1 kilometer per second. So it's cool, running a little soon. The accuracy as far as altitude is crazy accurate. It's usually within about half a meter, or it shoots up to where it's supposed to be. The landing accuracy was 16 centimeters average. It would be better, but when you watch it land, it actually bounces when the engine shuts off. So if we put some shock absorbers and we bounce, we should be able to land with about 5 centimeters of the target. And our poor concrete pad has been cooked to death. So there's a little bounce.
Cool.
That was a really good day. So yeah, there's for communication, it's on that tripod. You can actually like there, that's actually our communications. We just use off the shelf. Off the shelf is the key to new space. Buy stuff. Really, anytime you see something and you say, "Oh, I could build something that's better than that," you can't. If someone's selling, buy what they're selling. We use off-the-shelf Wi-Fi hardware for the communications. So on the vehicle is just standard, like you would see hanging on the wall, Wi-Fi router with little rubber duck antennas on it. On the other end, we just have there's a Wi-Fi router on the back of it. We use a directional antenna on a tripod, and Joel, our main investor, was actually pointing the tripod at the vehicle while it was flying. Works really well, so.
What is that, Zoe, brought to you by Radio Shack?
Have you ever flown it higher, like an altitude?
So yeah, that's what we'll be doing in the future, getting into altitude. Our waivers right now, we're only for like 250 feet. We're on an airport, which was a whole other debacle. So there was that. So level 1 had been accomplished. We really wanted to get done the first of our 3, but we ended up getting done the second, but it went really well. So that won us $150,000. That was the second prize in level 1. First prize was won by Armadillo Aerospace of Texas last year. So yeah, all that work and it paid off. It was fantastic. So of course the next thing. Then on October 23rd, so exactly a month after that photo I showed you of just the tank with us starting to put landing gear on it, we did the first static testing on Zoe. So we got basically from naked rocket to rocket thrust in a month, which was very quick. So here's, we were burning the midnight oil. This is 300 frames per second high-speed video of the first, or of, not the first, but one of the first static tests. I just find it nice because we're shooting the engine at some pavers so that we don't just dig a hole in the ground and they melt and fly away. I just find it really pretty. But, so they won't let us fly at night right now. I'm going to probably try to get a waiver so we can fly at night because they make for really cool videos. But for now, the static testing of little bits of concrete flying off it, near sonic velocities is pretty nice. So on Zoe, the major differences are that the tanks are about twice as large. The vehicle, the dry mass is a lot lower just because we got rid of the steel frame and all the unnecessary stuff. The plumbing system is basically similar. The controls, the computers, basically the same. And then one of the boxes exploded. We're running the tanks at about 600 psi, whereas on B they ran at about 530. The engine was originally designed at 750-pound thrust, and then we decided it was 800 pounds thrust. And on Zoe, we've run it up to 1,000 pounds thrust, so we say our engines go to 11. So this goes on for some time, but I just think it's nice. Big fireball, everything, because the plume is coming out supersonic. It trains air basically down almost the entire vehicle. So despite the fact that there's flaming stuff flying everywhere, the vehicle is relatively safe, and you can actually see like bits of frost falling downward, despite the fact that all of this gas is flying out in every direction. So this is also a video nobody's ever seen before because we were so busy that I haven't had time to put up any of this stuff online. So you guys are the first. So there's here I'll show you basically. This is the same test, not the same test, but a test on the same day. This is a full throttle run at about 1,000 We just had these concrete blocks, so we basically just chained it down to some blocks so it doesn't fly away. You can see like the general layout. The box on the top has the ACS, which shows the attitude control system. The little two black things sticking out are those Wi-Fi antennas just sticking out of a normal router. We switched to G for this vehicle, although I think we actually flew with G in the end. The box below it has the computer that's actually controlling. It takes instructions from the ACS on what it wants the vehicle to do, and then it actually sends out the, turn this valve on, turn this valve off, move this valve to here, that kind of thing. So, and then the module is a lot more integrated than it was on B, as like I said, 12 valves directly on it. But the key to us making really fast progress on it was to minimize what changed. So I really pushed to not change stuff that was working, and we were able to really turn this vehicle around really quickly. So.
Did you try doing like 10-second fires, turn it off, 10-second fire, turn it off, 10-second fire, like just keep pulsing it until you broke it, just to see how many times you could refire the engine over and over?
We haven't. At some point, we're going to do some durability stuff like that. The engine on Zoe, including the LLC, now has about 20 minutes of burn time on it, which for a rocket engine is a lot. You know, most engines, they do one flight into orbit or whatever, maybe 3 minutes, and then they're thrown away. So we haven't done. We did a lot of stuff on the test stand. I showed the Dash 1 engine, which is sort of our workhorse. It was the very first of the 750s, and it's still working. So it's not quite optimal. It has really high pressure drop in the jacket, but we use it for injector testing. One of the keys of our injector scheme is that you can actually swap out individually the fuel element and the box element, so that we can try all sorts of different customizations, try a bunch of different things to get our performance up. So our performance on the high end is about 95% of theoretical, which is actually really good. Getting full theoretical performance is almost impossible. Like the Space Shuttle main engine is basically the only engine that's ever made full of theoretical performance. So, sure. Question?
Ben, can you give like a 1-minute history from being a student to working at Masten?
Sure. Yeah. I'll.
And like what degree you got out and that type of stuff?
Yes. I'll play this one real quick, and I think I have 10 minutes, so I'm gonna try to, which is good. This is for all the staff tests. This is extreme throttle ability is one of the keys to being able to do VTVL, because the vehicle weighs a lot less when you land than it does when you take off. So, real quick, rifle through the slides and see what else I have. All right, yeah, well, I have 10 minutes and we want to get some questions, so I'll just kind of skip through some of the other stuff. So, very first flight of Zoe was the next day. We went from the static testing into the flight testing. The first flight was about 3 seconds. The second flight was 171 seconds. We didn't really have a lot of time to mess around with small steps. In the process of testing it before the LLC, we cut completely through a 4-inch concrete pad with rebar. The little sparks coming out, this is high-speed video, 300 frames per second. Little sparks are bits of rebar that are being vaporized and thrown out as sparks. The day before our first attempt at the LLC level 2, I actually was out there doing concrete work, filling the hole back in, and then putting some pavers in so that it wouldn't cut through the pad. So,
I was wondering, did you guys like bring out a bunch of stuff to make concrete? You seem to go through a lot of it.
Yeah, well, the pads we had poured custom, because the lunar pad, for the level 2, the other difference is you have to land on the lunar pad that has rocks and craters. And so we had somebody come out, a concrete contractor come out and do that. But this one we cut through the pad completely, not on purpose, just doing long duration flights right where the engine was impinging on the pad. So I ended up just patching it with some pavers and stuff. Let me see what else. So for our first attempt at the level 2, the first day we didn't fly. I don't know how many of you guys actually followed this stuff. The second day we flew. This is the landing in high speed again. You can see it's, like I said, it's falling concrete on the lunar pad. This is the first pad here, and that's the second pad in the background. And as soon as the vehicle landed, the composite fuel tank had been leaking fuel, and it was dripping down the LOX tank. And so as soon as it landed, it did that thing, and then almost instantaneously we got fire above the engine, which chewed through a whole bunch of wiring. Insulation on the LOX tank, which turned out to be slightly flammable, and the LOX tank's LOX in it, which is actually a good thing because the LOX is, negative 300 degrees Fahrenheit. You can basically put a propane torch directly onto the LOX tank with no issue. It'll just the LOX will suck the heat out so quickly. So then overnight we had some great volunteers. They completely replaced the entire wiring harness on the entire vehicle, which was insane. They got a plastic trash can lid and installed that under the fuel tank and ran a tube out of the bottom of it down one of the legs. So we couldn't fix the leak because it's a composite tank and you can't actually get inside of it to fix where the leak was. So basically just directed the fuel out where it wouldn't drip down onto the engine and light the vehicle on fire. So trash can lids, foil
It's a
tape.
catheter.
Yeah. Foil tape. The lid was held on by safety wire, which is the aerospace equivalent of baling wire. I mean, foil tape is like masking tape or like a duct tape, but better. So fire bad. And then we won. So the second day, after an incredibly long night, we had one more in the morning that the judges gave us. And so let me show, I'll just show the X-Prize Foundation video of that because it's pretty cool. I have a bunch more videos if you guys, if you see me at any point, I can show you. So here's the LLC video.
If you put full screen to YouTube, it might snap it to the right side.
I don't know where the full screen button is.
It'll scroll down.
So then this is the takeoff. You can see, like I said, it's a lunar pad with rocks and stuff, which we completely ignored because we just landed in the center. Take back off, and fly back up to 50 meters, fly back forward. So yeah, I went to Iowa State University for computer engineering. I was doing like one semester on, and I go to work for a semester and a half to pay for it. And then finally got sick of that and dropped out as basically like a junior maybe or a sophomore. Moved out to Mojave for 6 months and just bothered people until somebody gave me a job. So I'm sort of an example of persistence paying off.
And the truck got stuck.
The truck stuck, so I yelled at him and made him swap around. So that qualified us for level 2. This vehicle is light enough that we could just pick it up, so we just sort of pick it up and throw it back onto the truck, onto the trailer. And so those 2 flights won us $1 million, and that was like 2 weeks ago, 3 weeks ago.
Wow.
Then maybe you could talk about before that second flight, what you were busy doing with the clock ticking down.
Well, the first flight, some of the new plumbing that was replaced overnight, we had a couple of aluminum tubes that burned through that fed locks into the fire, which is all kinds of fun. But so the first flight, I was like hammering on a valve because I wasn't sure if it was working with the radio. It turned out to be working fine, so we did that. The second flight, one of the valves got stuck open, so it froze the igniter. So real quick, like right before the flight, I took the igniter apart, and then there was an issue with the time with the judges, which there's another whole story. But so I was like taking the igniter apart, and we retopped off the helium, and ended up with like 4 minutes to spare. So when we should have had about half of an hour. So when we won that, what we're doing next, altitude, flying higher and higher, hoping to do 10,000 feet within the next couple months. Aerodynamics, because we're going to be flying faster, so we're really getting more into air than we've done before. Vacations, that's why I'm here. Interesting trajectories, we have 2 vehicles. They can do all kinds of crazy stuff nobody's ever seen before, so I want to just do some interesting things. We can do mini gravity flights, basically where we fly at lunar gravity or fly at Mars gravity, which right now the only way you can do that on the Columbia Comet, and we can do it for longer durations. So it's scary trajectories. For the up and down thing, you can either re-enter tail first, and then you have to protect your engine against aero heating, or you can re-enter in nose first, which means that at some point you have to kick the engine on and flip the rocket over, which they call the death swoop. So that'll be interesting. And payloads. We're going to start flying payloads next year for low altitude stuff, not actually space, but so we're doing that. And then real quick, because I have you here, pick a worthy cause and dedicate your life to it. That's kind of why I'm here. I think that getting humans off of Earth is a key to, the survival of the species, which is probably a pretty common one here. But hedge your bets, do other things too. I started there's this Kiva org where you do micro lending. You loan $25 to somebody in Bangladesh or Indonesia or something like that. I've made 61 loans so far. We have a new space team. I'd like to say that we're beating NASA, except NASA doesn't have a team, so we're winning by default. It's at kiva.org/team/new space. Check it out. If you just happen to have to spare $25, the idea is you loan the money and you get the money back. So basically, you can help someone. It only costs you the use of $25 for 6 months. So I think it's a really good thing to do. Improve your solar system. So questions, or are we out of time completely? Or?
We are out of time. But if you want to stay here for questions, you're more than welcome to.
Sure.
We don't have to be in here. But the International Space University is happy